Okay. Suppose the inductance of an inductor is L and it's connected to an alternating EMF source E naught sine omega t. Okay, so the source will try to drive some current through the inductor. Can one of you tell me what an inductor does? What are inductors used for? Okay, see, inductor can store magnetic energy. That's one of the things it does. And inductors oppose sudden changes in current. Okay, it offers a back EMF which opposes a sudden change in current. Okay. Now, let's say at a random instant, the current passing through this loop is I in this direction, in the clockwise direction. See, the EMF is an alternating EMF. For some time, the current will flow clockwise, and for some time, it will flow anti-clockwise. Okay. What we need to derive is an equation for the current first. Then we'll have to find out the phase difference between the current and the EMF. Can one of you quickly recollect and tell me what was the phase difference between current and EMF when alternating EMF is applied to a capacitor? What is the phase difference between current and EMF when alternating EMF is applied across a capacitor?
So when EMF is zero, the I would be I naught. So like when one is
Peak.
minima, the other would be maxima. Like
Zero is not minimum. Zero is not minimum. -1 is the minimum of the sine function. Okay. What you said first is correct. When EMF is zero across the capacitor, alternating EMF is zero, the current would be maximum I naught. EMF zero is the mean value of EMF, not the minimum value. Okay. So when EMF is at its mean value, current will be at its peak. So how much is the phase difference between them?
Pi/2.
Pi/2, correct. And which function was ahead in phase? Current was leading or EMF was leading in case of capacitor?
Current.
Current. Current will have an extra phase of pi/2. So current will be leading the EMF by a phase difference of pi/2. We derived an expression for charge on the capacitor, energy stored in the capacitor. Okay, all those things. Fine. So we'll have to do a similar analysis here also. We'll have to derive the current equation. Based on current, you can tell how much energy is stored in the inductor. Average energy can be derived because the current keeps varying. No, we'll be interested in the average energy that it stores. Okay. Can one of you tell me a way to derive an equation for current through the inductor? We know how much alternating EMF is applied. Can you tell me a way to derive the current?
so dq by dt.
But we don't have an equation for Q this time. In case of capacitor, that's the idea. Because when alternating EMF is applied across a capacitor, we could write a function for the charge. Q is equal to C E naught sine omega t. We got the charge function, and from that we got the current function. In capacitor case, that could be used. But in inductor, we don't know the charge anywhere. What are some of the basic equations that we write while solving circuits? While deriving current in a circuit or something like that? Can we apply Ohm's law to an inductor? Can we apply Ohm's law and write an expression for current through the inductor? One of you tell me the equation of Ohm's law.
V is equal to IR, sir.
So Ohm's law helps you derive the current through what? Okay. See, in any circuit based problem, some of the basic equations that you will try to apply are Ohm's law, then Kirchhoff's current law and Kirchhoff's voltage law. Okay, these are the ones that will, these are the things that help you solve problems based on circuits. Now here I asked you a way to write an equation with current in it. Can we apply Ohm's law to an inductor?
No, sir.
No. It can be applied to a resistor, not an inductor. Kirchhoff's current law or the junction rule. Are there any junctions in this circuit? Clearly, there are no junctions in this circuit. Then we are left with one option, KVL. And KVL can be applied to any circuit. There's no restriction. Now tell me, if we apply KVL to this loop, will the equation involve the current or not?
It will, sir.
It will. Basically, KVL is that, KVL equation will be written like the algebraic sum of potential changes across all the elements or components in a loop is 0. Now in this loop, there are two components. One is the alternating EMF source and the other is the inductor. Okay, let's choose one point to begin from and one direction to move along the loop. Let's move clockwise. The first element we come across is the inductor. Isha, tell me, how do we write potential change when moving across an inductor in the direction of current? Or Rishi, if you remember, you can tell. Potential change across an inductor when moving in the direction of current.
Sir, minus L di by dt.
Minus L di by dt, correct. Okay. Therefore, the KVL equation for this loop becomes minus L di by dt. That's the potential change across the inductor. And across the alternating EMF source, it will be E itself. Okay. And should be equal to 0. That's all. Okay. So we get E is equal to L di by dt. And E, we have an equation for it. E naught sine omega t is equal to L di by dt. Send the dt this side and integrate. You get L di is equal to E naught sine omega t dt. Integrate both sides because our aim is to derive the current as a function of time. Integral L di will be Li. Actually, it will be Li with limits. Some initial current to current I equal to E naught. Can one of you tell me what is integral sine omega t?
Sir, cos omega t into omega.
No. You told the derivative of sine omega t.
Oh,
1
yeah.
by omega into minus cos omega t.
Correct. It will be 1 by omega into minus cos omega t. And from 0 to t time. Okay. So this becomes L into I minus I naught. We'll discuss about I naught later. Minus E naught by omega. Substitute upper limit cos omega t. Substitute lower limit cos 0. Cos 0 is 1. Okay. So what we do in this derivation is we relate this I naught to this 1. We cancel both of them. Okay. And then we get Li is equal to minus E naught by omega cos omega t. Our aim is to derive the current I as a function of time. Therefore, you can say I is equal to minus E naught by L omega cos omega t. That's all. We got the current as a function of time. Okay. Now, based on this current equation, we need to find out the phase difference between the EMF and the current. We should write an expression for the peak value of the current. In case of capacitor, if you remember, we found a new quantity called capacitive reactance, the opposition offered by a capacitor to current. Now tell me, from what you understand about inductors, does an inductor ever oppose current or not? Does an inductor ever oppose current or not? See, inductor is a, yeah, tell me.
It does oppose it, sir.
It does. Okay. Inductor is a coil. When flux through a coil changes, there will be an EMF induced in the coil, and the induced EMF opposes the change in flux. Now, flux through an inductor can change when the current through it changes. And when that happens, the inductor will oppose the change in current. If current is increasing, it will try to decrease it. If current is decreasing, it will try to support it. Okay. So inductor sometimes does oppose current. So we have something called inductive reactance. It's like resistance offered by an inductor. Okay. We'll discuss all those things. Understand how we got the current equation. Alternating EMF applied across an inductor. We just applied KVL for these two elements in the loop. Apply KVL, integrate those constant values, you strike off on both sides. You get I is equal to E naught by L omega. Okay, minus E naught by L omega cos omega t. The minus is very, very important. Okay. Now, let's convert this into a sine function. Why convert it into a sine function? Because the EMF was taken as a sine function. Now, if you want to tell what is the phase difference between them, which one is leading in phase or which one is lagging in phase, you should ensure the function is same first. Okay. So we'll try to write current in terms of the sine function. One of you tell me, minus cos theta can be written as sine of what?
-90 plus theta, sir.
90?
I think it's 90 minus theta or 90 plus, I'm not sure.
Sine 90 minus theta is cos theta itself. It's not minus cos theta. We want minus cos
90
theta.
plus theta.
No, sine of 90 plus theta is also cos theta only. Because sine of 90 plus theta takes the angle to the second quadrant. In second quadrant, sine is positive. And in fact, that is what we did in case of capacitor. In case of capacitor, we got the current as a cos function. Okay. Yeah, we got the current as a cos function. And you said cos theta is sine of theta plus pi by 2. That's why current had an extra phase of pi by 2. So tell me how to get minus cos theta. Sine is negative in which quadrants? Sine function is negative in the third and fourth quadrants. Now, if there's some angle theta, you want to change sine to cos. So you should add 90 or 270. Odd multiples of 90 should be added. Okay. So or you can subtract also. Plus 90, theta plus 90 you do, or theta minus 90 you do, sine changes to cos. But we want minus cos specifically. So we have to take the angle to the last quadrant. So you, from theta, what you do, you subtract 90. Okay. The angle will fall in the last quadrant, fourth quadrant. So sine has to be negative. So we'll get a minus sign. And because you are subtracting 90, sine changes to cos. So cos theta minus cos theta is sine of theta minus pi by 2. Okay. Anyway, I don't want to get into much mathematics. So you can write the current as E naught by L omega, and the minus cos function will be written as sine of theta. In place of theta, here we have omega t minus pi by 2. Is this step clear to both of you?
Yes, sir.
Rishi, understood?
Yes, sir.
Okay. The EMF function we had was E naught sine omega t. And the current function we got is this. We wrote both the functions in terms, both equations in terms of the sine function. Now, omega t is the phase of the EMF function, whereas omega t minus pi by 2 is the phase of the current function. So basically, the current function's phase is lesser by pi by 2. Lesser than the EMF phase by pi by 2. Okay. Therefore, what happens when you apply alternating EMF across an inductor is the current in the inductor, okay, IL stands for current through the inductor, lags the EMF across the inductor by a phase difference of pi by 2. Okay. Capacitor makes current lead the EMF by a phase difference of pi by 2. Inductor makes current lag the EMF by a phase difference of pi by 2. That's one thing. Next, look at the current equation that we got. We got I is equal to E naught by L omega sine of something, omega t minus pi by 2. Okay. Tell me, what is the maximum value of this function? Maximum current.
That E naught by L omega.
E naught by L omega. Okay. This is the variable part in this equation. And the maximum value of this variable part is +1. When this becomes +1, current becomes E naught by L omega. That means the peak current through the inductor is E naught by L omega. Fine. I naught is current. E naught is an EMF, peak EMF. Dimensionally, we discussed this in the last case also. Dimensionally, current should be voltage divided by resistance. Okay. Now, this is current. This is a kind of voltage. Then the denominator on the right-hand side, the L omega that you see, should be analogous to resistance. Right? But there's no resistor in this circuit. There was an inductor and a source of EMF. An AC source was connected. There is no resistance at all. So we don't call it resistance. What do we call it? We call it as inductive reactance. The inductor does oppose current sometimes, so it's kind of producing a resistance. We call it as inductive reactance, denoted by the symbol XL. Therefore, tell me, what is the formula for XL, inductive reactance?
L omega.
L omega. Okay. Unit dimensions and all will be same as that of resistance. Okay. If you remember last class, we had derived capacitive reactance, XC. XC was 1 by C omega. And now we got inductive reactance XL as L multiplied with omega. Okay. These are like something like a resistance offered by the capacitor and the inductor respectively. Okay. We got current, we got inductive reactance. Now, when current passes through an inductor, we know that some energy will be stored in the inductor. Can one of you quickly tell me the formula for energy stored in an inductor? Depends on inductance L and current I.
Half Li square.
Correct, half Li square. Okay. Now L is the inductance here, that's a constant. I is the current. Since the EMF is an alternating EMF, the current will also be alternating. As you see, the equation itself tells you. Okay, we got current as fine, minus E naught by L omega cos omega t. For some time, this will be positive. And for some time, this will be negative. The current we got is an alternating current. It keeps changing direction. And variable also, magnitude also keeps changing. Now, if current magnitude keeps changing, then the energy stored in the inductor also keeps changing. You can write it this way. Half L. In place of I am substituting I naught sine omega t minus pi by 2, where I naught is E naught by L omega, and you have to square it. So this becomes half L I naught square sine square of omega t minus pi by 2. That's the energy stored in the inductor at any time as a function of time we got. And you know this keeps varying. So we'll be interested in finding out the average energy stored in an inductor in one time period. Half is a constant, L is a constant, peak value of current is a constant. This is the variable term here. Can one of you tell me the average value of the sine square function?
So half.
Half, correct. Half and half, effectively it becomes 1 by 4 L I naught square. That's the average energy stored in the inductor. You can write it this way also. It's half L I naught square by 2, right? By 2 can be written as root 2 whole square. And what is I naught by root 2?
RMS.
IRMS, the RMS value of current. So you can equate this to half L RMS current squared. And once again, we see the meaning of RMS current. Usually, no, if a constant current I flows through an inductor, then the energy stored in it becomes half L I square. Now, when a variable current or an alternating current is flowing through the inductor, we got the energy stored in it as this. Now, this will be equal to this if the current is equal to the RMS current. So basically, for an alternating current, we can define RMS current this way. RMS current is the constant current which would make the inductor store the same amount of energy as this alternating current is making it store. Okay, so basically RMS value of current is the effective value of current in an alternating circuit. Okay, that's the meaning of RMS current. Okay, you can say it is the effective current in the AC circuit. Right. Okay, so we have discussed all three cases. What happens when an alternating source is applied across a resistor, applied across a capacitor, and applied across an inductor. Let's solve problems based on all this. And next class, we will discuss how to find out the current when L, C, R are all present, or even maybe two of them are present and all those cases. Okay, suppose there is a resistance, say 4 ohms. Alternating EMF is connected. Okay, wait, I'll change the equation a little bit. Instead of sine function, let's use some other function. Cos and omega t. Omega, I'll give you 100 pi t. Let's say this function already has some constant, pi by 3. Okay, so we are generalizing our equations. So resistance is given, alternating EMF is given across that resistance. You have to find out. First, write the current equation. Calculate peak current and RMS current. Then calculate average power dissipated by the resistor. Okay, solve this quickly. I'll give you 2 minutes. Okay. Current equation, anyone? Rishi, tell me, how will you relate current, resistance, and voltage?
Sir, Ohm's law.
What did you say?
Ohm's law, sir, Ohm's law.
Tell me the equation I is equal to.
I is equal to V by R.
And then why are you not doing that?
Sir, 1 second, sir. I'm sorry.
Okay, anyway, see, listen, both of you, it should not take this long. So you must stay in touch with whatever is being taught. Anyway, I is equal to E by R gives you the current through the resistance directly. Write the E equation as it is. Like whatever EMF is there, you have to take it. Plus pi by 3 divided by the resistance is 4 ohm. 10 by 4 is 2.5. So current is 2.5 cos 100 pi t plus pi by 3. Using this, you can tell the current through the resistance at any time. And see, the phase of the EMF function and the current function are equal. They will be equal across a resistor. Okay, we got current as a function of time. At least tell me these things quickly. What is the peak value of current? Look at the current equation and tell.
2.5, sir.
2.5 ampere. Assuming all are in everything is in SI units. Peak value of current is 2.5 ampere. Isha, tell me how much is the RMS value? Not exactly. You can keep the root 2 as it is if it is there. Okay, Rishi, you only tell me how to get RMS value of current.
I naught by root 2, sir, which is 2.5 by root 2.
Okay. So it's a cos function. For a cos function or a sine function, the RMS value will be the peak divided by root 2. So 2.5 divided by root 2 ampere. This is like the effective current in this circuit for power calculations. Okay. Then average power dissipated by the resistor. Tell me the basic formula for power dissipated by a resistor.
Sir, I square R.
Yeah, in terms of current, you can take it as I square R. But if the current is varying, if it's an alternating current, what is the adjustment you will make to that formula? Power is I square R if the current is constant. You can substitute that value. If the current is variable, you have to take the
I,
effective current. That's all. So 2.5 by root 2 whole square multiplied with R. Simplify it, you will get the average power dissipated, and that will be in watts. Okay. They can even ask you what is the current at a particular time. You substitute T there, you will get the current at a particular time. Once you know current at a particular time, you can tell what is the power dissipated at that particular moment. Okay, such questions also can be asked. Okay, Isha, is this clear? Any doubts?
No, sir.
Fine, fine. Let's try another question based on inductor. Assume the inductance is some 10 millihenry and the EMF applied is 20 sine. How much shall we take? Say 50 t. There's no pi. Okay, I'm directly writing it as 50 t. Or wait, let's not take the sine function. Make it cos 50 t plus pi by 3. Okay. So inductance is given. You are given the EMF function. First, calculate inductive reactance. Write the expression for peak current. Peak current will be peak EMF divided by XL. Okay, I'm giving you the formula also. Calculate peak current and then express current as a function of time. Yeah, do this first. Okay, I got answer, I think only for the first part, 510 power minus 3. We'll see. What is the formula for inductive reactance, XL?
Sir, L omega.
L omega, correct. L here is 10 millihenry. Milli is a factor of 10 power minus 3. Omega is 50. So 500 into 10 power minus 3. Fine. You can write 5 into 10 power minus 1. Unit will be ohms. Next, peak value of current. Directly from the formula you can tell. Peak value of EMF is 20 divided by 5 into 10 power minus 1. Becomes 40. Next, current as a function of time. Have any of you written the function? Okay, listen, since this is the first problem we are solving of this kind, current will generally be, see, it's an alternating current. Alternating current equation will be like this: I naught sine something, or peak value I naught cos something. One of these functions. Okay. Observe the EMF equation. EMF equation is written in terms of cos. Okay, and it has a certain phase, 50 t plus pi by 3. Now tell me what happens in an inductor. Will the current be in phase with the EMF? Will it lead the EMF or lag behind the EMF? Inductor case, the case we discussed today.
Oh, it lags, sir.
It lags behind the EMF by how much?
Pi by 3.
Not pi by 3, pi by 2. It will lag behind by pi by 2. Like in the derivation, we got minus cos, right? Minus cos was written as sine of theta minus pi by 2. So what happens here? You need the peak value of current. Peak value is already calculated, 40. Then write the EMF function as it is, not function, the oscillating part of the EMF function, that cos part, 50t plus pi by 3. And the current should lag behind the EMF by a phase difference of pi by 2. So just subtract pi by 2 from the phase, that's all. That is the current equation. All you need is peak value and an oscillating part. Peak value you got. Oscillating part, take it from the EMF function and make adjustments with the phase. Simple. And you can like change, I mean, you can convert this to other functions if you want. Now, if this whole thing is called as theta, cos of theta minus 90 becomes sine 90. Okay. So you can write it as, wait, what did I say? Not sine 90, sine theta. Cos of theta minus 90 is sine theta. So this can be written as 40 sine 50t plus pi by 3 also. Now there's no restriction as to which way you should write it, but if you are attempting an objective exam, then you have to be careful with the options. Okay, so while solving problems, what you should do is take the EMF function as it is, make adjustments for the phase. Like here we subtracted pi by 2. Look at the options now. If this option is directly given, you will choose that. Suppose options are all in terms of the sine function. Then you'll have to convert this cos function of current to a sine function, which can easily be done. But that comes with practice only. You need to know exactly theta plus pi by 2 becomes what, theta minus pi by 2 becomes what, all those things. Okay. We got current as a function of time. That's fine. If you know current through the inductor, then you should be able to write energy in the inductor. Tell me, how much is the average energy stored in this inductor? Inductance was 10 millihenry. This is the current equation. How much is the average inductance? Average energy stored in the inductor. What's the formula for energy stored in an inductor? General formula. Isha, what is the formula for energy stored in an inductor?
Sir, is the answer 4 what is it? I don't know the
Okay,
unit,
tell the
sir.
formula.
The average formula is 1 by 4 Li naught square.
Okay, you can write it that way. See, general formula for current energy stored in an inductor is half Li square, right? So if an alternating current is flowing through it, you can write it this way: half L I RMS square. Just take effective current of this AC. That's all. So half L is 10 milli, 10 into 10 power minus 3. RMS value of current squared. Peak value of current is 40. RMS will be 40 by root 2 and you square it. 40 square 1600 into 10 is 16,000 into 10 power minus 3 becomes 16 divided by 2 into 2 is 4. Answer is 4 joules. That's the average energy stored in the inductor. Is this part clear? Any doubt in this?
No, sir.
Okay, now you all tell me, what is the minimum energy stored in the inductor at any instant, and what is the maximum energy stored in the inductor at any instant? You know, it's a varying current, so energy in the inductor will also be varying. What is the minimum and maximum energy? Any idea to calculate the minimum energy stored in an inductor?
Sir, do we just take the least minima or something and then substitute and then find it?
Wait. Do we take the minimum of?
The like instead of the peak, I don't know how to explain it, sir.
Tell the formula for energy in an inductor.
1 by 2 Li square.
Half Li square. Okay. In an AC circuit, which term in this equation will be a variable? Or which term on the right hand side will be a variable?
Sir, the current.
The current. We want the energy to be minimum. Therefore, that will happen when the current is minimum, because I is in the numerator on that side. Whenever that is the least, the energy will be the least. Okay. Actually, not the current. The square of current should be minimum. Okay. Now you have a sinusoidally varying current. what is the least value of its square?
Zero.
0, correct. The minimum value of the sine square function is 0. So see, current keeps oscillating between minus 40 and plus 40. We found that the peak value of current is 40. Okay. So current keeps oscillating between minus 40 and plus 40. Somewhere in between, it touches 0 also for an instant. Now, whether numbers are negative or positive, their squares are going to be positive. So to get the minimum of I square, you have to take current as 0. So the minimum energy stored in the inductor is also 0. At a particular instant, it won't have any energy in it. Okay. One of you tell me, how will you get the maximum energy stored in the inductor? Obviously, energy will be maximum when I square is maximum.
Yeah, sure. So it will be uh,
Half L, what will you multiply it with?
sir 40.
Square, 40 square.
Yeah.
Okay, fine. 1600 into 10, 16,000, 1000 and 10 power minus 3 will get cancelled. 8 by 2, sorry, 16 by 2 is 8 joules. 8 joules is the maximum energy. 4 joules is the average energy. Minimum is 0. Okay. Let's solve one problem based on capacitor also. But remember remember how to write the current equation. Get the peak value because we know current equation is going to be of this form. I naught sine something or cos something. So it's important to get the peak value and then just find out the phase. Peak value, you know how to calculate. If it's a resistance, E naught by R. If it's a capacitor, E naught by XC. If it's an inductor, E naught by XL. That will give you the peak value of current. Then the phase. If it's a resistor, EMF and current will be having the same phase. Write the EMF variable part as it is. Like the oscillating part of the EMF function, write it as it is. If it's a capacitor, you know capacitor makes current lead the EMF. So take the oscillating part from EMF, add a pi by 2 inside the phase. That will become the phase of the current function. If it's an inductor, like the problem that we have solved now, take the oscillating part of the EMF function, subtract pi by 2 inside the phase bracket. Simple. So try this now. Suppose there's a capacitor. I'll give you the question in reverse. Current equation will be given. You have to write the EMF equation. Let's say capacitance is some 20 microfarad. Some alternating EMF is applied. And we see that the current through the capacitor is, let's say 2 cos 100. Shall we include pi? No need, because omega has to be there in the, okay, let's not include any pi. Cos 100t plus pi by 4. Current equation is given to you. You can see the peak value and all. Okay, first get the peak value of EMF, then write the EMF function. Do this part.
Sir, I got the answer, but I'm not sure if it's right.
Okay. How did you try to calculate EMF? Don't give me the answer, but tell me the steps.
Sir, so 1 second. So E naught is equal to XC into I naught.
I naught is E naught by XC, so E naught will be XC
Yeah.
multiplied with I naught, correct?
Yeah. So then which becomes 20 into 2 into 10 to the power minus 6.
What becomes 20 into 2 into 10 power minus 6? XC is not C.
No, so I naught is 2, right?
I naught is 2.
Yeah. And then so it becomes 20 into 2 into, because that the capacitance is in uh and mm,
Did you calculate XC? That's what
yeah,
I'm
sir.
saying.
Oh no, wait, I might
Uh,
have not.
that's what I'm saying. XC is not same as capacitance. Isha, how to calculate XC?
Sir, I did I naught is equals to C naught omega.
Okay, from that you fine, nothing wrong in that, you can do. Yeah, I naught is equal to C naught omega. So 2 is equal to C is 20 micro, 20 into 10 power minus 6. E naught omega is 100. Can be done. Even if you calculate XC and solve, you'll get the same thing. This is, I think, simpler. Good, good. So E naught becomes, the 2's cancel, this becomes 10. 10 into 100 is 1000. 1000 into 10 power minus 6 is 10 power minus 3. Send it that side, it becomes 10 power plus 3. Isha, is this what you got?
Yes.
Okay. So peak value of EMF will be 1000 volts. Rishi, did you understand?
So can you explain once more?
See, you wanted to use I naught is equal to E naught by XC, right?
Yes, sir.
And the formula for XC is 1 by C omega. C omega goes to the numerator. You get I naught is equal to C E naught omega. From there, we derived E naught.
Oh, okay, sir. Understand.
Okay, can be done. Okay, now we need to write the EMF function. See, EMF function generally will be of this form. Some peak value, then a sine bracket or a cosine bracket. I mean, some oscillating part will be there. Peak value and an oscillating part. Peak value we derived already, it is 1000. How to write the oscillating part? Anyone? How are current through a capacitor and EMF across the capacitor related in terms of phase?
Sir, when one will peak, the other will be 0.
You have to tell exactly which one, or you tell which one leads and by how much.
So when EMF is 0, I naught will be at its peak, and then it'll lead by pi by 2.
So current leads the EMF by a phase difference of pi by 2. Okay.
Yes, sir.
If current leads EMF, it indirectly means EMF lags the current. Okay. EMF
Yes,
is
sir.
behind current in a capacitor. Now we know the oscillating part of the current function. We'll take it as it is, cos 100t plus pi by 4. And current will be leading, means EMF will be lagging. So you have to subtract pi by 2 from it. That's all, simple. Okay, once you get the peak value, you just have to adjust the phase of the other function to get the phase of this function. And this can be written in other forms. Like effectively you have cos of theta minus 90 degrees. Cos theta minus 90. Theta minus 90 goes into the fourth quadrant. Fourth quadrant cos is positive. So this becomes sine theta. So you can write this as fourth quadrant cost is positive only, no? Yeah. So this simply becomes 1000 sine 100 t plus pi by 4. You may be given this option, which is correct. Okay, so you should be comfortable converting cos to sine, sine to cos and all. Okay, so did you all understand what all we did today? Like what happens when alternating EMF is connected to resistor, capacitor, inductor separately? How to find out currents, energies, average power dissipated, all those things. Is it clear? Any confusion anywhere?
No, sir.
Okay, but I can see you people are struggling with what do you say, the basic formulas and conversion of sine to cos also. So tomorrow's worksheet you'll have questions based on all three: resistor, capacitor, inductor. Solve it thoroughly and send. Like, I can tell you are not solving the worksheets because I mean the way you are answering, it's not satisfactory. Kind of like this, like stuff we discussed in the last class, you should be very comfortable when you come to this class. So I know you are going through some other chapter in school, some chapter here that will be there. But see, you have what? This is October, November, December. You have three months, maybe a 10 days extra. So you have 100 days for your first JEE main session. Now you can't say, sir, I am studying that, so I am not able to study this and all. Everything should be in your mind. Okay. So put some extra effort. And see, this is not very difficult. I mean, what I am explaining to you is not very stressful also. I'm taking classes on alternate days only, no? So one day is for class, the other next day is for revision. So you have to ensure that from now onwards, you don't forget anything that you study. Today, or not today, last class, the class before that, and today, we derived some equations, alternating EMF applied to resistor, capacitor, inductor separately. Do those derivations on your own. Okay. From EMF function, practice writing the current function. From current function, practice writing the EMF function. All this will come in very handy for our next class. Next class, we are going to discuss LCR series circuit. Okay, when multiple components are placed in the alternating, like when multiple components are connected to an AC source, how to find out current, how to find out energy stored in them, power dissipated by resistor. So practice thoroughly and come for the next class. Okay, thank you all. We'll continue on Saturday.
Thank you, sir.
Thank you, sir.